Welcome to the Chameleon Testbed for Computer Science tutorial. My name is Junyi Chua, and I will introduce you to the Chameleon Testbed and show you how to use it to run your computer science experiments. To do this, we will go over a very small and simple experiment together, one that measures the performance of Spark. What is Chameleon? In a nutshell, Chameleon is a testbed for computer science experimentation. A testbed for computer science experimentation must be deeply reconfigurable so that a user can work on it as if they had it in their lab. Users should have access to up-to-date and fine-grained information about the resources. Users should be able to reserve nodes, have root access to the machines, the ability to reboot them, power them on or off, boot from custom kernels, and have console access. It is also important that users are isolated from each other so that experiments run by one user do not affect another user. This property of isolation is also critical to support repeatable and reproducible experiments, because if your results are affected by external factors, the results may vary in ways that you cannot control. Chameleon is large scale. We wanted to make the testbed as large scale as we could afford in order to support a range of experiments including big data and big compute research, otherwise known as HPC. Consequently, the testbed was designed to include 650 nodes for a total of almost 15,000 cores, with most of them concentrated in a large homogeneous partition to support HPC experiments, and 5 petabytes of storage for big data experiments distributed over 2 sites connected with a 100 gigabit network for large flow experimentation. Chameleon is complementary to other testbeds that already exist, such as Genie and Grid 5000. We support identity federation with Genie. Last but not least, Chameleon is an open testbed that seeks to support all non-commercial research projects. Getting access to Chameleon is easy. Just request an account and apply for a project. You will get an answer within 1 business day, and you will be on your way. Find out more at chameleoncloud.org. The building block of Chameleon hardware is what we call a standard cloud unit, a rack composed of 46 Intel Haswell nodes. We have 12 of those racks distributed between 2 sites, University of Chicago and the Texas Advanced Computing Center, or TAC, connected by a 100 gigabit network. They form a large homogeneous partition that can support large-scale experiments. To store experimental data, we have roughly 3.5 petabytes of global storage. And finally, we also support heterogeneous hardware at smaller scales to vary the types of experiments users can run. Full specifications of hardware are displayed on this screen. Standard cloud units, or SCUs, form a large homogeneous partition. Each SCU has 42 compute nodes, and each has 2 Intel Haswell processors that have 12 cores, for a total of 24 cores per node. There are 4 storage nodes, with 16 2-terabyte disks per node, for a total of 128 terabytes per each rack. We have 128 terabytes of disk with very high I/O bandwidth per rack. At over 12 racks, this totals 1.5 petabytes of storage. Allocations can be an entire SCU, multiple SCUs, or within a single SCU, or even across SCUs. For example, we could make a Hadoop cluster out of storage servers with a high I/O bandwidth. The 3.6 petabytes of storage where you can save your experimental data is configured as an object store with dual replication, and is also used to support an image server. All of this has already been deployed. In 2016, we focused on deploying heterogeneous hardware. Some of the heterogeneity will be added on top of the current homogeneous hardware. One rack already has InfiniBand, so that you can experiment with both InfiniBand and Ethernet. Others have high memory, non-volatile memory, SSDs and HDDs, so you can experiment with different types of storage and storage hierarchies, GPUs, and FPGAs. In addition, later this year, we are hoping to release Atom microservers and ARM microservers. How is all of this hardware configured, and how can you access it? We developed infrastructure called CHI, or Chameleon Infrastructure, which allows you to reserve isolated nodes, reconfigure nodes at bare metal level, reboot, power on or off, and have console access. There are 2 ways to use Chameleon: via the web interface, which we will mostly present in this tutorial, and via the command interface for advanced users, or if you want to use scripting. The Chameleon project started in October of 2014 and had a public release in July of 2015. As of now, we have more than 1,000 users and 200 fantastic research projects being developed on it. All homogeneous hardware has already been deployed, and the heterogeneous hardware is gradually being deployed. We have two types of resources: bare metal resources, which are our main offering and the subject of this tutorial, and we also provide a KVM OpenStack cloud for education and application projects. ARMS and Atoms will be deployed later this year. All basic capabilities are currently available, and we are working on extending them, as well as making it easier and more efficient to run computer science experiments. We're counting on your feedback. Find out more at chameleoncloud.org. The objective of this tutorial is to teach you Chameleon basics so that you can run groundbreaking experiments. You must have a Chameleon account added to the webinar project and a Unix-like operating system with the ability to use SSH keys. We will guide you through the steps of creating a very simple experiment. You can follow along and do the exercise, or you can listen and use the Chameleon Bare Metal Guide to recreate this content. If you get lost, refer to the Bare Metal User Guide or ask a question via the chat channel. To access the Chameleon Bare Metal Guide, go to chameleoncloud.org. In the Documentation tab, click on Bare Metal, and you'll be taken to the Bare Metal User Guide. During today's experiment, we will measure how Spark performs in terms of CPU usage, with a state-of-the-art platform providing enough CPU resources. Spark is an open-source data processing framework that extends the MapReduce concept and can be used to process large amounts of data. We will use Spark Perf, a benchmark suite dedicated to evaluating Spark's performance, to understand how well it performs. We will visualize the metrics. Each of you will be able to run this benchmark on Chameleon, generate usage charts collected from metrics using Ceilometer, and present them as graphs using an Apache 2 server application. This is a very simple experiment designed to give you a framework for how to use Chameleon for computer science experiments in general. You can modify and enhance this simple experiment later on to work on your own projects. Now let us talk about experimental workflow. A typical experimental workflow will include the steps depicted on this diagram. First, we must design an experiment to compare performance. We determine our benchmarks and we determine our resources. Next, we try to find suitable resources. We will show you how to reserve resources to make them exclusive for us. Then, we proceed to configure and interact with these resources. We run the performance evaluation, monitor various qualities, get data, and finally, analyze results. Sometimes we will return to step 1. In our case, we already know what we want to experiment with. We want to evaluate the performance of Spark, and to do that, we will run a specific benchmark. So now we can go to the next step, find the resources we will run on, and go through the steps in the 4 green boxes. We will do it during this exercise. Let's discuss the process of discovering resources and describing them. Descriptions of resources need to be fine-grained, down to the serial number of individual components, so that researchers can understand every detail of the testbed. These descriptions also need to be complete and up-to-date, so that if a resource modification was made, such as exchanging a drive, everyone will be informed. Descriptions must be versioned so that we don't have to compare individual parts by serial numbers. We should be able to know at a glance from which version of the testbed our results were obtained. And even if we cannot reproduce them exactly, at least understand the difference between the different configurations in which the experiments are run. Before accessing the Chameleon testbed, please note that all steps that will be described during this webinar are described in our Bare Metal User Guide that can be accessed by going to chameleoncloud.org, clicking on Documentation, and then clicking on Bare Metal to see the Bare Metal User Guide. Because we want to measure how Spark performs in terms of CPU usage, we plan to measure it with our state-of-the-art platform providing the necessary CPU resources. Chameleon provides such a platform, so why not do this experiment leveraging Chameleon resources? But before planning to use some resources on Chameleon, we need to reserve them. I will describe the steps that will enable you to reserve resources on Chameleon. However, if you feel lost or if you want to do the webinar at your own pace, you can follow the instructions on the Bare Metal User Guide. All Chameleon physical resources available to users are described in the Chameleon Resource Registry. Users can consult the registry via the Resource Discovery portal at chameleoncloud.org/user/discovery. It is also accessible from the Bare Metal User Guide in the Discovering Resources section at the link Resource Discovery Web Interface. On this page, you can get a description of resources available in Chameleon. You can select different criteria. Here, we can select nodes in the Chameleon cluster located at TAC, containing 2 CPUs that can handle up to 40 threads each. Once you click the View button, you get a description of all servers matching your selection. Each node is listed independently and a list of hardware components is drawn. Each component is fully described, including the serial number, such as the chassis serial number. For example, in this description, we see that the CPU used in this node is a Xeon E5-2650V3 at 2.3 GHz. With this information, we can retrieve very precise characteristics of the CPU in the CPU database provided by Intel. We must make sure that our description is up to date by using semi-automated node discovery. When a node is added or updated, a script can automatically collect information about its components. This not only prevents human errors, but also ensures that the information is made available to both users and the resource manager as soon as any change or update takes place. Each modification of a component and each update causes a new version of the Chameleon testbed to be generated. It means that if you ran an experiment 6 months ago and don't remember exactly how the testbed was configured then, it is possible to retrieve the state of the Chameleon testbed as it was 6 months ago. You can access the versioning thanks to a web service based on a REST API. I will give you an example. If you want to get all the changes made on the Chameleon cluster located in TAC, you can run a terminal command. The response is a long JSON dictionary. I will give you some details about the response we got. First, we can see that 32 changes have been made on the Chameleon cluster located at TAC since it was first deployed. Second, the last change appears in the dictionary. And according to this response, we can access details of the value using the following command. We see that the last modification was related to adding nodes with FPGA boards. As we saw a few minutes ago, each bare metal node of the Chameleon testbed is described precisely in a resource registry. Each official image provided by the Chameleon testbed includes CC checks, a tool that is in charge of checking that the resource matches its description. This tool will be introduced later when we have a running instance. We have looked through Chameleon resources, and we have discovered the resources we are going to use. Chameleon supports getting those resources on demand. However, if you want to reserve a very large partition, for example, the whole testbed, you typically cannot do it on demand because some other users may be using these resources, so you need to request them sometime in advance. Resource requests are fine-grained so that you can request them by node. In this segment, you will learn how to create a reservation in order to conduct our Spark experiment using Chameleon resources, and we will see how the users are isolated from each other. If you want to learn how to reserve resources on Chameleon, and you want to follow the instructions at your own pace, you can still follow our bare metal user guide. To be able to use Chameleon resources, they need to be reserved for you. It can be done in the Chameleon dashboard. In a web browser, log in on the Horizon web interface. For TAC resources, go to chi.tac.chameleoncloud.org. For University of Chicago resources, go to chi.uc.chameleoncloud.org. You will need the same credentials that you used in order to sign up for this webinar. You should land on the Compute Overview page for your default project. The pie charts on this page will show you the current usage of things like instances and public IPs as relative to the limit for your project. You can select the project that you want to use via the list at the right of the logo. In this guide, we will use the CHI-817790 project, but any project will work the same. You can also set your time zone in the User Settings page. I am in the Central Time Zone. To reserve resources, click on Reservations in the left bar, and then Leases. Click on the Create Lease button. It should bring up a web form which enables you to request a lease. Here you can make reservations in advance. In order to run large experiments using a lot of resources, you can select the starting date in the future. You can also start a lease as soon as possible. On this form, there is a Reserve Specific Node text field, where you can enter in the ID of a specific node. This enables you to do several experiments using exactly the same hardware. This is very useful for experimental reproducibility. Pick a name for the lease. This name needs to be unique across your project. In this example, we use my first lease dash, then my username. Pick a start time. If you want to create your lease soon, pick a start time in the near future. Pick an end time. Choose the minimum number of hosts. It is 1 by default. Choose the maximum number of hosts. It cannot be less than the value used for your minimum number of nodes. It is also possible to reserve specific node types, such as those with InfiniBand support. We will reserve a compute node, which is the default option. When you are finished, click the Create button. Once created, the lease details will be displayed. At the bottom of the page are the details about the reservation. Initially, it is in the pending state and stays in this state until we reach the start time. Once the start time of the lease is reached, the lease status will turn active. You may need to refresh this page to see this. Resources that you use on Chameleon are isolated. Each bare metal node can be used by a single user at a time. To illustrate this, you can click on the Lease Calendar button. On the x-axis, we have time. On the y-axis, we have individual nodes. In this page, you can see multiple colored horizontal bars. Each bar represents a lease of a specific node. We see that some bars have the same color. They belong to the same lease, which spans multiple nodes. With this isolation, we limit interferences that an experiment belonging to user A can have on experiments belonging to user B. You have now obtained a lease, a temporary ownership of some Chameleon resources. But how can you access this lease securely? How can you configure it? How can you verify that the resources in this lease are indeed the ones that you have asked for? In this section, you will learn how to access your reserved Chameleon resources securely, how to deploy an image, how to assign a public IP to this image, where to find images and how to create them, and once you have deployed an image and logged into your instance, how to verify that the resources you received are indeed the ones that you asked for. Again, if at a moment you feel lost or if you want to follow the instructions at your own pace, refer to the Chameleon Bare Metal User Guide. Once the lease is active, we are almost ready to start an instance. By creating a lease, you reserved some resources on Chameleon. However, to prevent other users from accessing your resources, Chameleon needs a way to be sure that you and persons authorized by you can use these resources. The most common way is to use a public-private key pair and to connect via SSH to the resources. To be able to perform such a connection, we first need to set up a key pair. This only has to be done once per project. There are 2 different ways you can create SSH key pairs and access to your instance. This will depend on the operating system that you are using. Let us start with Unix and Linux since the processes are very similar. Open a terminal window. In OSX, click on your Launchpad and search for Terminal. In an Ubuntu system, you can use the keys Ctrl-Alt-T if you have the desktop version of Ubuntu. First, access the SSH key pairs directory. In your terminal, type the command cd space //.ssh. To create your SSH key pair in the SSH directory, type the command ssh-keygen space -t space rsa space -b2048 and hit enter. After completing the previous step, a message stating enter file in which to save key will be displayed. Enter the name of your preference. In this example, I will use the name sample-key and press enter. Next, you'll be prompted for a passphrase for your key. Entering a passphrase is not necessary, so you can proceed to leave it blank and press enter. You'll be prompted to enter the same passphrase again. Press enter, and your public and private key pair will be saved. Since we are still in the SSH directory, now you can see your newly created key pair by typing ls. In here, you will see two files, sample key, which is your private key, and samplekey.pub, which is your public key. You will need to provide the public key to your cloud system or individual instance. In a browser, from the Horizon web interface, to add a key pair, first click on Compute. Then click Access and Security, and click on the Key Pairs tab. Next, click on Import Key Pair. In this window, you will only need to provide a name for your key pair and paste your public key in the public key window. To obtain the contents of your public key, access your local SSH directory through your terminal and type the following command: cat sample-key.pub. Select and copy the contents displayed, starting with SSH-RSA and ending with the hostname. Paste the contents into the public key window. Then click Import Key Pair. Whenever you are creating an instance in Chameleon or OpenStack, you will have an option to select the public key you just imported. Once selected, this public key will be inserted into the instance's known hosts file. When a user attempts to connect to the instance, the private key provided by the user will be validated against the public key in the known hosts file. Now that you know the mechanisms on how SSH key pairs work, you may want to connect to your instance. To do so, you can use the command ssh-i/.sh/sample-key space cc at, and then you would enter in the instance's IP address, which we will assign after we launch an instance. So we will come back to this later. For now, let's go to the instances panel. Click on the Launch Instance button in the top right corner. Select a reservation in the reservation box. Pick an instance name. In this example, we will use my first instance-jchua. In Instance Boot Source, select Boot from Image. And from the image name, we're going to select Webinar. If you have multiple key pairs registered, you need to select one in the Access and Security tab. Finally, click on the Launch button. The instance will show up in the instance list, starting in the build state. It takes a few minutes to deploy the instance on bare metal hardware and reboot the machine. After a few minutes, the instance should become active and the power state should be running. At this point, the instance might still be booting. It might take a minute or two to actually be accessible on the network. In the meantime, we can attach a public IP to the instance. When an instance boots, it is put on a private network. To put it on a public network so that you can log in, we need to assign a public IP to it. Public IPs are sometimes called floating IPs because each IP may be reused for many instances in turn. Click on the drop-down menu to get the actions list. You should see Associate Floating IP. You should get a screen allowing you to assign unused floating IPs. If there are no unused floating IPs already allocated to your project, click on the plus button. In the window that opens, select the ext-net pool if not already selected by default, and click the blue Allocate IP button. Finally, click on the blue Associate button. This should send you back to the instance list, where you can see the floating IP attached to the instance. The floating IP will enable you to interact with the resources that will host your Spark and experiment. You'll be able to launch experiments and collect results. Let's look at the Virtual Appliance Catalog. The Virtual Appliance Catalog is available on chameleoncloud.org. Click on the Appliances link. This appliance catalog enables users to launch pre-configured instances on the Chameleon infrastructure. Virtual appliances can be created by any user of Chameleon and made available to other users of the infrastructure. By clicking on Comps 1.3 CC CentOS 7 appliance listed in the Appliances catalog page, the user is redirected to the description of the virtual appliance. This particular appliance was created by researchers working at the Barcelona Supercomputing Center. This image contains all the tools that are required to launch Comps, a task-based programming model developed by Barcelona Supercomputing Center. By leveraging the appliance catalog, they are able to share their work with a community of users that can, in one click, instantiate their work, test their tools or frameworks, and provide feedback. By clicking on the Launch at Kai at TAC link, the user will be redirected on the corresponding image in Chameleon dashboard. Clicking on Launch Instance will bring up a page containing the instance creation form. While we were assigning public IPs and talking about the catalog, the image has been deployed and the instance is now available to log into. You should now be able to connect to the instance via SSH using the CC account at the floating IP that was assigned to the instance. In a terminal window, type ssh-i tilde.ssh/sample-key space cc at the floating IP. In our example, this would be 129.114.108.215. You will probably receive a warning message. Type yes and hit enter. You should arrive at a prompt like this one. If you encounter troubles with the connection to your instance, you may take a look at the troubleshooting section of the bare metal user guide. Let's verify the resources that we requested. We can now check whether the resource matches its known description in the resource registry. To do this, simply run sudo space cc-checks space -v. In this section, you will learn how to use Chameleon monitoring facilities to monitor experiments such as our Spark experiment. Now that we've checked that the hardware is correctly configured, we can start measuring the CPU usage of the Spark framework. We prepared scripts dedicated to running a Spark benchmark and to producing experimental results. To launch the Spark benchmark, log in to your instance. And then please run the following command: sudo bash run benchmark. It will configure the node with a stressing tool based on a benchmark dedicated to the Spark framework. In addition, the above script will start a web server for convenient interactions between users and this node. The web server should be accessible at the address provided during the creation of a floating IP. Typing this address into a web browser should result in the following web page. This page contains two links. The first link leads to a public web folder that can be used to access visualizations produced by the computer. The second link goes to a web application that depicts metrics of the Chameleon node. To generate metrics, we use data collected by Ceilometer. Now we will show you how to visualize such metrics. The first step is to load a script to reach the OpenStack API. Source Chameleon rc.sh. The script will ask you for your Chameleon username and password. Now we will generate figures displaying the metrics supported by Chameleon by running the following command: bash update metrics.sh. You should get this output. In your web browser, browse to your Chameleon IP's floating address /cc. This should lead to this page. Click on the first link, and you'll get a figure close to this one. Congratulations, you just measured the CPU usage of the Spark benchmark. This benchmark shows that the Spark framework can be very CPU intensive. Thus, it requires a state-of-the-art platform providing high-performance CPU facilities, such as those found in the Chameleon testbed. We hope that this first experiment on the Chameleon testbed convinces you of its experimental potential to enable beautiful experimentation for computer scientists. Now just a few words on Chameleon Organization. Chameleon is organized as a set of research and education projects. Those projects are associated with an allocation for Chameleon resources that users on those projects can use. Each project has to have a principal investigator, or PI, who is typically a professor or a scientist leading a research group. The PI proposes the project by filling out a web form and gets a reply within 24 hours. Once the project is approved, the PI can add users to the project who get access to an allocation on Chameleon resources. I created a webinar project for the webinar today. You all joined the project and thus were able to access Chameleon resources. In order to access Chameleon in the future, you will need to create, or ask your professor to create, a new Chameleon project reflecting your research. Then you can carry out work on this project. Whom can request projects and how is described in our FAQ, available on the chameleon.org website. From the chameleon.org website, if you are logged in, you may also access your dashboard. Once a user is connected to Chameleon Cloud into the Chameleon portal, they have access to the user dashboard. This is a page that enables them to both gather information and manage profile information, projects, and remember that a user may be a member of more than one research project, reported outages, help desk tickets, as well as other webinars. Information about outages is available at the outages page. It enables users to get current information about outages that are happening now or are past outages. The help desk page enables users to report the issues they encounter with the Chameleon infrastructure. By clicking on the Create New Ticket button, users access a form where they can provide details about the issue that they are facing. In addition, we have a users mailing list where users can ask each other's advice, share relevant information, and interact with each other. You can keep abreast of what is happening on Chameleon via our news channel or RSS feed, or via social media where we publish information about new features. Happy experimenting. Create a project and start experimenting. Remember to share your appliance with others when it is ready. We look forward to hearing about your research. And remember, the most important element of any experimental testbed are our users and the research they work on.